longest carbon chain beats out calling this a tert butyl on a shorter carbon chain. And we're not spending a lot of time on bicyclic structures. We will see bicyclic molecules or polycyclic molecules. Some of you have bicyclics, but the spiro, the fused, and the bridged bicyclics, they're not easy to look at their conformations. They're not easy to name. They just clutter our time, and I would rather you guys have stronger foundational skills that you could approach these if and when you need to with your foundational skills than weaken your foundational skills and try to get you to be aware of all of these or try to master all of them. We left off yesterday looking at the conformations of cyclohexane. So, can anybody remind me how to draw a chair structure for cyclohexane? Good. 2 diagonal lines. You said one longer than the other?
Yeah, so like the bottom up. Like
Yeah.
Offset.
Offset from each other. They can be the same length.
Yeah.
Actually, it's better if they're the same length. One good idea is to do your first line and then come about halfway down and draw the same line again. Now on the side that's pointing down, whichever direction that might be, what do I connect them with? Yeah, an upside down V. Upside down V, or as I call it, an up V. And then on the side that's pointing up, how do I connect them? A normal V, a down V. Are these the same thing? Yes and no. I gave you guys that website the other day, yesterday, SimOtter, where you can look at the chair conformation. One of your classmates brought a website to my attention yesterday that I've actually added to our homepage. This is a link to a 3D molecule generator called MoleView. On MoleView, you can draw your own structure. So you can see I've drawn this one. I'm going to restart and just draw a cyclohexane. And you'll notice that even though my top-down view just looks like a hexagon, flat, MoleView knows that this 6-membered ring has a preferred lowest energy chair conformation. How do I get it to draw it in a boat conformation? I don't know. I just found this website yesterday. So you might not be able to get this to be drawn in a boat conformation. You might kind of be stuck like this. So use it as you'd wish to help you visualize 3D structures. The other conversation I had after yesterday's class was chair conformation is really not a good name for this. It doesn't look much like a chair. I think the idea is that it looks a little bit like a lazy boy. But it's not a chair that I would sit in. So I like the term bolt conformation. It does look like a lightning bolt. But I wonder if maybe boat conformation and bolt conformation are just too similar. And boat works really good. We could call it the bowl conformation. Bowl conformation and bolt. Now they're still pretty close. Now we put some descriptors on our chair. We looked at all 6 of the carbons and we broke them into 2 groups. Up carbons, down carbons. There's 3 of each, and they're pretty easy to find. Up carbons point up on the page, down carbons point down. What we didn't do yesterday were draw in the positions that come off. We did name them. We said that on an up carbon, there is a group that points straight up, and that's true on every up carbon. And on every down carbon, there is a group that points straight down. Then, on every up carbon, there's a group that's mainly equatorial. It looks like it's kind of in the shape of the equator of the ring, but it actually points more down than it does straight out. So we call it down equatorial. Up axial, down equatorial. Down axial, up equatorial. Now, drawing these can be a challenge. So I actually do my best to avoid having you draw chair conformations when it's worth a grade. Because I don't want to say I don't trust your ability to draw a chair conformation. I just don't know if we have enough time to hone in that skill so that you get all the points that you're due. But I do think that there's a benefit to being able to sketch it on your own so that you can make predictions and find the right answer. Yeah? So that's why I still want you to be able to draw these so that you have the skill of drawing it. One thing that they say about these equatorial groups is they're actually parallel to a line that's like one bond away from them. So here's an equatorial group. It's meant to be parallel to this line. Here's an equatorial group. It's meant to be parallel here, which means this line will be parallel to this equatorial group, and this line will be parallel to this equatorial group. The regions on a chair conformation where it gets really challenging to draw in groups is actually on these center two positions. The corners are kind of nice, but the center two, you lose perspective. It gets really hard to draw them. Anyways, this group should be parallel to this line, which means it's going to end up looking like that. We know because it's a down carbon that this is an up equatorial bond, but it looks so similar to this down axial, just opposite. We lose some of that perspective. It's a challenge. We get the same thing here. It should be parallel to this bond, which means we get something like this. These are by far the hardest positions to draw, those center two carbons. So sometimes you need to be a little bit careful and maybe even note it for yourself. I'm drawing this to be down equatorial, and I'm drawing this to be up equatorial, just so that you don't ever mistake what you're drawing.
So are the blue and red the hydrogen bonds?
You know, we could throw in anything we want to,
Okay.
but since this is cyclohexane, we haven't substituted it yet. Yeah, these would all be hydrogens at the end.
Okay.
Actually, if we leave it like this and we assume bond line structure, they're all methyl groups, which is a very sterically strained molecule, but doesn't mean that MolView can't generate it. Oh, except it made that little isopropyl group there. Look at that. That's easier to look at, right? Actually, here's an interesting thing. The chair conformation is gone. Oh no, there it is. It's kind of a warped chair though. And those methyl groups are just adding a lot of steric strain on that molecule. So it's hard for it to take up its normal shape. I'm going to get rid of those because that is tough to look at. One thing that I do want to say about chair conformations. There are no wedges or dashes. A lot of students want to try and imply it. Well, I've got an up group, and up is wedged. I've got a down group, and down is dashed. But we have agreed that with these projections, there is an assumed stereochemistry, and we simply do not show wedges or dashes on chair conformations. So I'll encourage you to avoid it, only because I think it can hinder more than it can help sometimes. Okay, so cyclohexane has two chair conformations, which are separated by a boat conformation, which means that we can represent the relationship between these two conformations with an equilibrium arrow. A chair conformation needs to go into a high energy boat conformation before it can relax into a different chair conformation. This is actually not unlike what we saw with Newman projections. If I want to go from a low energy staggered to a different low energy staggered, I have to go through a high energy eclipsed conformation in order to rotate. But we would say that the two chair conformations of cyclohexane are equal in energy. They experience the same amount of strain. Now let's look at substituted cyclohexanes. We'll start with our mono-substituted. Let's take something like methyl cyclohexane. Now I've added a wedge there, but if it was a dash, I think you'd agree they're the same molecule. I could take a spatula under this and flip it like a pancake, and that methyl group stays at the same position, but is now pointing backwards. So a wedged group or a methyl group, it means the same thing. But later when we get to poly-substituted groups, wedges and dashes will give us information about where to put it in our chair. Wedge should equal up. If you see a wedged group, draw it into your chair conformation up. What type of positions are up? Sorry? There's an up axial, and there's an up equatorial. So it matters then only, am I putting it on an up carbon or a down carbon? An up carbon has an up axial, and a down carbon has an up equatorial. But either way, this group is up, always. Cardi B helps us remember this by saying if it's up, then it's up, then it's up, then it's stuck. You see an up group, it's going to be up in your chair conformation. Well, this molecule has two chair conformations. So I'm going to draw two chair conformations. Now, I have demonstrated that there are two ways to draw chair conformations, but you can draw them exactly the same way and still represent the molecule differently. Active might not agree with that. Active might say that if they give you this conformation where it's slanting up, and it wants you to draw the second, you need to draw the conformation where it's slanting down. I'm not a big fan of that because that really is just a matter of rotating your perspective on it. But I'll tell you what we can use to help us distinguish our two structures. Doesn't matter where I start. In fact, it doesn't matter where I put my methyl group. So I'm going to go for one of these corners, and I'm going to pick this back right corner. This back right corner is an up carbon. So my up methyl group will take the up axial position, and what will go in the down equatorial position? The hydrogen on that carbon. Now, I'm not going to draw anything else because it's just going to clutter the structure. We'll use bond lines to say CH2, CH2, CH2. And of course, this is in equilibrium. There is this the energy enough to make these molecules flip back and forth. Now, I don't have a methyl group on this molecule, but what I do have is a hydroxyl group, so it kind of acts the same as our substituent. Here it is on that up carbon, taking its up axial position. This molecule is now going to flip into a boat, and then it will flip into another chair. I'm just going to make sure my carbons are all pointing the right way. Do you notice how this looks different than before? Is the OH group still up? Oh, a lot of shaking heads. What is this position? Down axial. So what is this? up equatorial. If it's up, then it's up, then it's up, then it's stuck. It's always up. But what did it flip between? Axial and equatorial. Actually, I want to point out another thing. This is the same carbon. But is this an up carbon now in this new chair conformation? It's now a down carbon. So I can't draw my methyl group on this up carbon anymore. It's not on an up carbon anymore. It's on a down carbon. So I'll pick another down carbon and I'll draw my CH3 up equatorial. So here's what happens between chair conformations. We call these chair flips. Chair flips result in all up carbons become down. And vice versa. All down carbons become up. All axial groups become equatorial. I had an up methyl, an axial methyl, and the molecule went through a chair flip, and now it's up equatorial. What doesn't change? Groups stay up or down. We're talking about two things, carbons and groups. Up carbons become down carbons. Axial groups become equatorial groups. But up groups stay up groups. Up axial to up equatorial. So which of these two chair conformations has a higher energy? We'd have to look at steric strain. And in order to get a picture of steric strain, it's best if we actually look through a Newman projection. So I want a Newman projection that has these substituted carbons kind of right on the Newman projection. And remember, because we're looking at a cyclohexane, anytime you sight down a carbon-carbon bond to get a Newman projection, you're going to end up getting kind of this double Newman projection. So I'm going to sight down this bond and this parallel bond. I think you guys would agree that I could have sighted down these parallel bonds as well. But I'm going to do it this way, and I'm going to take my perspective from this side. Two Newman projections. Two little eyeballs. On the right-hand side, I need to address something. I think I forgot yesterday to also mention there is assumed perspective with the rings. Whatever is on bottom, that's closest to us. So when you need to put yourself in the plane of the board, this is on your left-hand side, this is on your right-hand side, away from you. Take it out, put it down. I've got a CH3 that is straight up, and an H that is down to the right. And that's on my front carbon. On the back carbon, I have a CH2 with one H up to the right and one down axial H. This back carbon then has an up CH2 that connects to the down or the back carbon on the other Newman projection. So back carbon, CH2, back carbon. Remember, the big circles are back carbons on the Newman projection, and I've got 2 back carbons. And from that back carbon, I guess my molecule here is flipped. Let me spin this on mole view so that you guys can see it the same way. From my back carbon, I have this up CH2 that connects to the other back carbon. On the front carbon, I've got this down CH2 that connects to the other front carbon. And then all of my other positions are hydrogens. There's a lot more going on than just the linear chain Newman projection, correct? We've got to kind of look through all of this clutter. I'm not necessarily encouraging you guys to erase this in your notes. I might erase it in my notes to bring us back down to just one Newman projection. But if I cover up this Newman projection on the left, I can actually start to make some steric assessments again, just ignoring all of that. Look at this methyl group on the front carbon, which is adjacent to this CH2 group on the back carbon. That's steric strain, the same way we identified it in our other Newman projections yesterday. This is also steric strain, a CH2 on the front carbon and a CH2 on the back carbon, but that's always going to be there, whether it's cyclohexane or not. So this is really the unique steric strain. This is given a name. I don't bring it up often, but that name is 1,3-diaxial strain. The reason it's named that is because this axial group now has a steric environment here with the other axial carbons. They're now competing for space on the top of the ring.
So could you say that would be gauche too, or are those different molecules?
Yes, this is steric strain caused by gauche non-H groups, a CH3 and a CH2.
Oh, yeah, I can see gauche as steric.
Yes. All right, now let's do the same thing here. I can't look down the same bonds, because if I did, I wouldn't be noticing the steric environment here. So this time I'm actually going to take this perspective. I'm going to sight down this Newman projection. Once again, 2 dots right next to each other. This time I don't have to do so much crazy work moving this molecule in and out of 3D space. I just look at it right here. On my front carbon, would you agree I have a down axial group? Down axial hydrogen. And I have an up equatorial methyl. This front carbon connects to this front carbon by an up carbon. Up connects the 2 front carbons. And all of the other positions on this Newman projection are hydrogens. H, H. Oh, that's not totally true. I did lie a little bit. Because the 2 back carbons connect by a down carbon. Are you guys okay with this? You hate it? Good. Oh, sorry. This is art class. Would you agree? I mean, we are really just taking perspectives on 3-dimensional objects. Enough of this like 2D molecule stuff. These are real 3-dimensional objects. Any steric strain? Let's look at what the methyl group is around. This is the same. The up and down carbon, that hasn't changed. But my methyl group is gauche to H and gauche to H, and it's anti to the rest of the ring. No steric strain. So here's our big takeaway. Axial groups always generate more steric strain than, I can't say more without saying than. Axial groups create more steric strain than equatorial groups. Okay, here's a really nice takeaway. You can draw a structure, a chair conformation, or draw the 2 chair conformations for a molecule. And in each of them, count the number of axial groups. The structure with less axial groups has less strain, is more stable. More axial groups, more strain, less stable.
Quick question on the right.
Mm-hmm.
Aren't those CH2s next to each other?
Yes.
But that wouldn't count steric.
These 2 CH2s are gauche to each other, which does create steric strain, the same amount that's in every chair conformation. So we're kind of looking at novel steric strain generated by the substituent groups.
Oh, okay. So
Yeah.
You see like an actual laid out substituent instead of steric strain.
Yep. Now again, this is a hydroxyl group which substitutes really well for the methyl group. They both are non-H groups. And when this group is axial, like we see here, then it starts to interact with everything else that is axial. That's the steric strain. And when this flips, and it is kind of hard to flip it, you're going to get this like every other carbon goes from down to up. When it flips, do you notice how that OH group now just sticks out away from the molecule? It's not fighting for space at the top of the structure, but by being equatorial, it has alleviated a lot of its strain. We can do this for any group. Tert-butyl, bromine, carbonyl, aldehyde. Anything you want to put as a substituent there, it's going to be lower energy when it's equatorial.
Would it be okay to equate the word equatorial with lateral? Because you're coming out to the side?
Lateral sounds like a biology term. Is that true?
I
Your
don't know, just
lateral-
Like whenever I picture something going left to right, I think lateral.
Yeah, I think lateral works.
Okay. I don't know, because I mean, that just makes more sense in my brain.
I think the reason they chose those terms was because this ring looks a bit like a sphere. Here's the equator of it, and here is the axis. And so any group that is parallel to the axis that you spin around, those are axial groups. And any group that is more or less parallel, literally up or down, to the equator of it, we call equatorial. You could call them lateral if you want to, but you won't find anybody else that calls them lateral.
I guess what I'm saying is that term isn't like necessarily wrong.
Nope, I
in
don't think
its
so.
definition,
I agree.
even though it's not common.
I do think that if you have an anatomy background, lateral might mean something to you than if you don't have an anatomy background. So different people might interpret lateral differently. But I do agree, like, it does mean kind of side to side, right? Then alternatively, maybe you could call vertical groups instead of axial groups,
Right.
because they are directly vertical to the axis. All right. Let's move from mono-substituted rings to poly-substituted rings. there's one important thing I want you to hold on to. The stereochemistry of the groups matters. So those wedged groups all need to be up. Those dashed groups all need to be down. All wedges are drawn up. All dashes are drawn down. But the sequence also matters. Their relationship, clockwise or counterclockwise around a ring, matters. If you have a wedged group and a dashed group, and they're kind of related clockwise, wedged to dashed, you can't draw them in the chair related counterclockwise, wedged to dashed. It changes how the molecule physically takes up space, so we need to pay attention when we convert these top-down views into our chair conformations, and vice versa when we take a chair conformation and convert it into a top-down view. So now I've got two substituents on here, and here's the challenge that I would like us to do. Given one chair conformation, I want us to draw the other chair conformation, and I want us to draw the top-down view. What would it look like as just a flat hexagon wedged and dashed? That can give us a lot of information too. So I'm going to put a CH2Cl up axial, and then I'll put this OH down axial. Sorry, up equatorial. Did not mean to say down axial. I say we start by drawing the top-down view. So I'll draw my hexagon. And maybe I'm not sure yet about wedges and dashes, but I can be sure about their relationship. I need to have a carbon with CH2Cl, and then clockwise, a carbon with OH. I can't put OH CH2Cl. I have to put CH2Cl OH. Just being mindful of how they are related to each other in space. CH2Cl, axial, up, correct? Up, axial, which means it will get what in the top down, wedge or dash? A wedge, because it's an up group. OH, best described how? Up equatorial, which means it gets what shape in the top down? Up. Up is wedge.
Oh, yes.
Equatorial doesn't tell us much. Up tells us everything. Would you have guessed that they were both up? Not at first glance. You've really got to put in the work to get used to practicing. This up axial group is wedged. This up equatorial group is also wedged. All right, now let's change our chair conformation. Let me give you a better chair conformation. What do I need to make sure happens when I flip my chair into this second conformation? Good. My CH2Cl needs to go from up axial to stay up, but become equatorial. What should I do with my carbon then can I choose any carbon to place my CH2Cl group on? My CH2Cl group started on an up carbon, so it needs to end up on a down carbon. So I'll put it here. I'll keep it nearby. And it's going to go down axial, correct? CH2Cl? No. If it's up, then it's up. But now, up is up, equatorial. Now I can put my OH group on this carbon, correct? That changes their relationship spatially. So I need to have the OH group go here. I can't have CH2 to OH and then have OH to CH2 going clockwise. They've got to have the same relationship. OH is going to go in what type of position on this up carbon? Up equatorial, up axial. Down equatorial hydrogen. You got a question?
No, I'm just sorry.
That's okay. I know it's kind of hard to see it from back there. Both of my groups stayed up, but they have successfully transitioned from equatorial to axial. Okay.
So are we also, we've changed the conformation, inverted it, I guess.
Yeah.
And then have we also rotated it like one click?
You know, it's hard. I mean, you want to keep this up carbon in kind of the same corner, but now make it a down carbon. I hate to say there's actually no way to do that. So here's that up carbon in that top right corner. You want it to be a down carbon now, which I guess would be here, but actually the top right corner is still kind of an up carbon. So even if you take diagonal to the right and you flip it so that it's diagonal to the left, it still feels like you're kind of twisting it around a little bit. This carbon is now this carbon, which still feels like it's kind of rotated. But you are right. Diagonal to the right, diagonal to the right. I've kept the carbon chain exactly the same. And all I've done is, clicked those carbons around one position. One position to the right. One position to the right.
For the sake of drawing it, for the sake of being able to visualize what's going on.
And it ensures that all of my up carbons are now down, and all of my down carbons are now up. Excuse me. Good question. Belen. I'll draw it for you. But, you can put it on any position as long as it goes to a down carbon. So let me give you a couple of other options. Instead of this, but keeping with the same structure, I could have put this CH2Cl on this down carbon. And then the OH still has to be related the same way, rotationally. So now it's going to go up here, right? CH2 to OH clockwise, CH2 to OH clockwise. This and this are the exact same structure, just rotate it around a little bit. And then on this guy, I could put it here. Here's my up equatorial group, down axial, and then my up axial group, down equatorial. Did I answer your question? Yeah. This is the same as this, just with a slightly different orientation in space. That's all you're doing. Maddie.
So if we put the CH2Cl on a down instead, would that be a different compound?
Yes. If either of those groups was dashed instead of wedged, it's a different molecule. We'll actually talk about the relationship, the name that we give it.
I'm having a hard time visioning when you circled at the top with you drawing that down.
Oh, I did screw up, didn't I?
Yeah,
Thank
it's
you.
really like messing with.
That's because it's wrong.
Thank you.
Thank you for pointing that out. What is wrong about that?
It's a different
Yeah, because the CH2Cl is not up anymore. And it needs to stay up. If it was up at any point, it needs to stay up. So how do I fix that? Swap the H and the CH2Cl. Yep, sorry. That's a good catch. Now they're all the same structure. Before it was different. You were trying to get me to notice that, but I had no idea.
Well, I mean, I was actually just asking that question.
Which of these two chair conformations is higher in energy? The one where the CH2Cl is equatorial? Or the one where the CH2Cl is axial? Why? Okay, well, this has one axial group, one equatorial. This has one axial group, one equatorial. So both chair conformations have the same number of axial groups. So can you give me another reason why this would have more steric strain? Here's another thing I want to add. Look at this Newman projection. What do you notice about the OH and the CH2Cl? They're gauche to each other. They create additional steric strain. Now let me flip this again. What do you notice about the OH and the CH2Cl? They're still gauche to each other. They still have steric strain. So those two groups are going to create gauche steric strain no matter what their position is. But here, the OH is creating steric strain by being axial. And here, the CH2Cl is creating steric strain by being axial. Hayden?
Doesn't like the electronegativity of the hydroxyl have something to do with the energy as well? It's in the center, to the right side.
You know, there is something to be said about oxygen's lone pairs, its electronegativity, and ways that can impact stability. But that's a little bit more complicated. Like with sugar molecules or other structures, we won't have to get that deep. What we can say is that when chair conformations are tied, with the same number of equatorial groups in both structures, higher strain comes from a larger group. Now, I don't want you to have to guess at what's a large group and what's not. So it'll be really obvious. As a group gets more and more atoms, it becomes a larger group. Methyl, very small. Tert-butyl, the biggest. How would you guys compare the OH and the CH2Cl? Yeah, the CH2Cl is going to cause more steric strain. CH2Cl, greater strain than OH. So if I wanted to say my most stable chair conformation, my lowest energy chair conformation would be which one? Sorry? Where the CH2Cl is equatorial. You got a question, Jamie?
Yeah, doesn't it like get to a point like if you have a CH3, isn't that gonna be
Bigger than OH?
no, like that's still gonna be smaller than a single bromine, right? Because of the size of the atom.
Yeah, I've seen different tables report more or less precise values. For instance, one table said chlorine, bromine, and iodine all cause about the same steric strain. Surprising, because iodine is much larger than chlorine. I would not have said they cause the same steric strain. And then other places that say OH, the halogens, CH3, they cause roughly the same amount of steric strain. So I'm not trying to get you guys to have to guess. Is OH larger than CH3? Is CH3 larger than bromine? where does it tip? I'll try to make it very obvious. You've got a chlorine against an isopropyl. Isopropyl has a CH and 2 CH3s. That's a much larger group. Tert-butyl, very large, especially compared to a methoxy, OCH3. So in a way, I might say you could try to count the atoms, but that's a little bit dangerous. I would say each carbon group is about equivalent to each other group. OH, about equivalent to a carbon group, about equivalent to a halogen.
So like, what about a CH3 versus a CCO?
A CCl3?
Yeah.
A CH3 versus a CCl3?
Yeah.
It's hard to say, but 3 chlorines on there is probably going to increase it. Kind of like how 1 chlorine here made a big impact too. Brett?
So just to clarify, the reason why that is the lowest one is because the CH2Cl is in between the 2 hydrogens? Does that have to do with
No,
that
it's not
strain?
because it's between the 2 hydrogens. That's just an artifact of us drawing it.
Okay.
It's because it is equatorial. When that group is axial, we can take a Newman projection and show that this axial group is causing steric strain on these other axial parts of the ring.
Mhm.
But when it's equatorial, the smaller group is causing that steric strain, and this one is not.
Okay.
Russ?
So is it true then that, as a general rule, if something is equatorial, it is lower energy? Or is that more a relationship of what else is in the ring?
It has to do with everything else. So, yes, each group, when it's equatorial, is lower energy on its own, but then you have to consider the cumulative structure. OH is at a lower energy when it's equatorial, but because that causes this group to be axial, the molecule at large is higher in energy. The molecule at large is lower in energy when OH is at its highest energy.
So the total steric strain versus the steric strain of that group.
Correct. Total steric strain of the structure compared to what that little group is experiencing.
But what it contributes largely depends on if it's axial or equatorial.
Yep. Exactly. All right. Let's do another one, shall we? Let's take this top-down view. Let's draw both chair conformations and decide which of them is the lowest energy chair conformation. That is a wedged CCH3, which could also be called tert-butyl. Start by sketching out your 2 structures, your 2 chairs, and then you really get to choose where you start. Pick any carbon and call that carbon the group with methyl. And then figure out how methyl is going to show up on the carbon you chose. It's a shortcut.
You pick the hardest spots to go to. And the issue I would say is that this is a down carbon, but I don't see any groups coming down here.
So it's a wedge that you're
Well, yeah. The turbule, the H ones.
Oh, I think you want the
Yeah. But the problem is that on the down carbon, I see no down axial group. And on the up carbon, I see no up axial group.
and that's another SDH. Right?
That would be true.
Oh, so if I fix the H's.
Yeah, and quite honestly, it doesn't matter what the groups are. It's enough carbon that has no constituent.
Oh, that's so tricky. The wedges and the dash.
Yeah.
So it's kind of like inverse neutral.
No, I mean, you did draw this up group up, but then the assumed down hydrogen is not drawn down.
Right. Oh, okay. So.
Like what you have here, actually. That has an up axial group. You just gotta show the up axial group.
Oh, so I can drop through.
Yes.
Oh.
Yeah. Now you got their orientations correct. But would you agree that this is 1, 2, 3, 4, and this is 1, 2? So their relationship is not drawn correctly. If you choose this to be 1, where would position 4 be? 1, 2, 3, 4. I don't know what that is. Here, they're related correctly. You've got CH1, 2, 3, 4. But here, they're related 1, 2. Mm-hmm. And then the other thing that I would say is get rid of the wedges and the dashes. They're going to be just straight lines in the chairs. Top down, they need to have them. But this is correct. Once you get that fixed. Yep. Yeah, it's looking better, but would you agree that this kind of looks like it's up, but equatorial, not quite axial? You would have to be just straight up in the bottom. If anything, this should be more out to the side. It gets cluttered, and I do get that. It's the same here, actually. This is a down carbon, so it should have down straight. Up, straight. Instead of that.
Yeah, I went the other way. I started like
Well, yeah, if you added those cells, that would be good. But you got a turf butyl up
My
position
mind
one,
is down and
and then a
it's
renal up
throwing
position
me off.
two. Instead of having one more. You could show the turf butyl here.
So the wedges are up,
I
and then there's
So I did
four
that.
positions apart,
Yeah.
right?
4 carbons.
So it's really awesome because like I did it here, so it's like I'm up carbon, so it's up back.
You got it right.
like you can ask it like
That's 4 cells.
yeah.
Up carbon toward it.
But
But then you can do it.
now I'm up. Does that make sense?
Then you have 1 and 4.
Right.
I think
That's really good. It's just that it's on the
exactly like mine. Yeah, we did exactly.
Maybe.
It's not so we can.
You're on a good start.
I just have to
Of where it was like.
The reason I know you have it.
Yeah, so
Right.
It's very heavy, so I was like in pain. My nails is always like. Sorry.
Good. Great. And you know which one is lower energy. Good.
So it's
Great.
sealed.
Yes, great job. Perfect. You got it. Yeah, this one I would draw your blue line more straight down.
Oh, okay.
It's down axial. And the same with this H, straight
Straight
down,
down.
down axial.
Question on this, the green are the most stable ones.
Okay.
Is that right? Because I accidentally circled the wrong one.
Yeah, this one's not most stable. This one is most stable.
Oh, so it was the orange.
Yeah. Maybe just say orange.
So it is the orange.
The orange one is the most stable.
Oh, but the green ones are the lowest energy.
Lowest energy is most stable.
Is it safe to assume you're asking like which is the most stable position? If we took just like a quick glance, the biggest molecule in equatorial position, that's green, right?
Yeah.
So the second one is gonna be the lowest energy.
You talking about this?
No, like
Well,
the
I don't
one-
know.
The ones that we had.
Did you circle it?
No, I didn't. Like this one would be the lowest energy.
That's right.
Yeah, sorry. So,
Yep.
Oh yeah.
Perfect.
this one is gonna be up equatorial.
Yes.
And then this is gonna be, this is where it's confusing.
Down equatorial. But your H should be straight up.
That's where I saw.
That would be the only thing to fix. Yep.
Thank you.
It's a good start.
So, I mean, really, if you're changing conformations, you're just going from axial to equatorial, but you're staying in the same form.
And I was like confused because it was like
Up or down.
CH3 is down. That's the
Good.
axial.
Did you find the lowest energy?
Yeah.
Good. Which you can say is because you're doing projection, but now we can
The
jump
second
past
one
it.
and all of them
Yeah,
are the
that's
lowest
okay.
energy, most stable.
Yeah,
And all three that we've done.
Wait.
Good. Good.
Yeah, I don't think it's gonna be like that all the time, but like basically.
No, but like as far as the
Yeah,
some
as
people
far
like
as it is, I'm sure it's pretty common. But yeah, like Russ. What do you guys say? Like if the biggest molecule is equatorial,
Now, which one is
That's why I asked him, like, so it's safe to say if you ask what's the most stable.
Yeah, and it's a little challenging to know which one is axial.
We just take, find the biggest molecule because they're in a equatorial position, and he said, yeah, this is the safest.
okay.
This is an upper.
Second, yeah, okay. So
Good.
Just find the biggest molecule, find it in an equatorial position, and that's gonna be your most
I'm
stable.
running out of colors. You know what's sad? Sad is I do have erasable highlighters too. These aren't them.
Erasable highlights.
Yes.
Pens are awesome.
Oh, I know. Like I cannot. I mess around with the computer too much, trying to figure out how to make it do what I want. So
I think you got and you got up.
I know, I was sitting
You're
and
not actually
trying to
making
put
it
together, but like the colors for doing this.
Yeah.
Yeah.
So awful. Down.
Yeah.
Like, yeah. Like this part like breaking down and like putting what
I
each.
really like it.
That's the nice thing about the iPad. Is like I just put it in games.
Yeah, I'm just an idiot with that stuff because I'm old and I'm not used to it.
Sure.
Like
What
last
I've
time I
done
was
is
in
I
school,
just loaded it
10 years ago,
There's,
like Canvas
problems
was not.
I have with your change stuff.
I haven't done that yet. Yeah. So we're gonna do that. I'll start our midterms will be
Yeah. Oh, no, yeah, for learning it, like, up practice, when it's just like tracing the change, and then we'll erase it. It's really helpful.
You want to go to
I just worry
maybe
that.
to down.
Yeah.
But I
Here
think
versus on hand, it's gonna be.
This
Yeah,
down.
yeah, I'm with you.
Okay. Good. Yes. The only problem is you went from up turbinal to down turbinal. Down methyl to up. So actually, if you physically flip this, and I don't know if you can do that with like do it horizontally, but otherwise, what I would do is take this methyl group and put it on this carbon, take this turbinal group, put it on this. You did go from up to down. Oh no, you haven't actually. You did from up to up. You went from down to down.
Yeah, my chairs are just not like perfectly muted.
No, it's okay.
But they're still up.
But that's the problem. So turbinal starts on an up carbon. Now it needs to be on a down carbon.
This is a very hard topic. You're kind of dyslexic.
No. It goes to a down. It stays. This is up axial.
Yeah.
Now it needs to become up equatorial.
That's how I have to be there, because I look at these charts and you're like,
I want to keep its orientation up.
Yeah, because
we're just talking about a radius in space.
That's
yeah,
correct.
and that's literally like on the.
So this
One, two, three,
Correct.
four, and then just switch it to 1, 2, and then they all.
All right, guys, let's
But that's how I have it.
look at this together. So, their relationship in space is 1-4, and it actually doesn't matter if you look at that clockwise or counterclockwise. But I did see a few people that had one structure where they were 1-4, and then the next structure where they were 1-2. So I want you to pay attention to maybe counting your carbons, mapping them out, and making sure that you do keep them 1-4 to each other. The other important thing is that whatever is carbon 1, if it's down or up, it needs to flip in the other chair conformation. So it needs to start down, it goes up. Or if you start it up, it needs to become down. And it doesn't matter which way you kind of click it around. You could do a full 360, kind of like we did up here, as long as you keep your groups oriented the same. Then you need to make sure that the groups keep their relative position. Up tert butyl, I've decided to start on a down carbon. What position is up on a down carbon? Equatorial. All right, I'm going to actually sketch it out. I know a lot of you wrote it in there as CCH33, which is not wrong. I want to demonstrate that you can change it how you want to. And then just to clarify that that is up equatorial, I'm going to draw a nice straight line down for my down axial H. And now at position 4, straight across the ring, I've got a down methyl group. What position is down methyl on an up carbon? Down equatorial. And I can clarify that by having a nice straight line up for my up axial H. Some of you played the hardest game possible, and you chose these to be your positions 1 and 4. And it's really challenging to show which group is axial and which group is equatorial when you go to these positions. The nice thing, though, is you know it's a down carbon, so whichever bond is drawn pointed down on the page is axial, and whichever bond is drawn pointing up on the page is equatorial. You know it's an up carbon, so anything up you know is axial, and anything down is equatorial. That is the most challenging part, but what I want you guys to avoid if you do go to these spots is avoid having these groups come out like this. Notice this up carbon has 2 down groups. Where is its up axial? Nothing is drawn up. That's the error. This down carbon has 2 up groups. Nothing is drawn down, and that's the error. But if you can avoid it, I would advise it, because it's just the hardest spot.
So I get that we're talking about like the same molecule in different orientations in space.
That's part of it.
Is there going to be any, and I know that there's like different strains and forces pushing within the same molecule to have it be sitting in different shapes, but is there going to be any difference in like function or behavior of this molecule depending upon its shape and orientation?
Actually, yes. There are reactions, especially with alkyl halides, that cannot take place in certain chair conformations and can only take place when that halogen is oriented axial versus equatorial. So the conformation does play into reactivity.
Okay. And what kind of outside influences cause the molecule to be in what shape they're in?
Mostly heat, energy. You provide more heat, you provide more energy, you increase the statistical odds of that molecule having the energy required to go through a chair flip, to go into a boat conformation and come out in a different chair. That's our chair flip. So you provide more heat, you provide more energy to do that, more chance that you get it into the conformation that you need. All right, so here I have elected to move my carbons clockwise. I just as easily could have moved them counterclockwise, except that would have put me in the middle carbons, and I'm not here for that. Tert butyl is up. Now it's on an up carbon, so straight up, I've got my CCH3 group, and I'll clarify that that's straight up with my down equatorial hydrogen. Straight across the ring, I've got down CH3, clarified with my up equatorial H. Which is my lowest energy chair? Why? Most equatorial groups. It does help that tert-butyl is equatorial, because really I wouldn't even look at methyl. I'm prioritizing tert-butyl being there. But it is convenient that all of my groups are now equatorial.
Aren't the boats supposed to be like a mirror image of each other?
They don't have to be. They absolutely can be. That's where we've got diagonal lines going up in different directions. But in my opinion, there's no benefit to it. And I think I have a force of habit for drawing it a specific way. And so if you're good at drawing chairs a specific way, keep it up. But if you can draw them opposite ways, it isn't going to hurt. Actually, that was what I tried to get at here. I've got my chairs going in the same direction. But I could have drawn my chairs here. I could have drawn my chairs opposite, which means these are the same thing. The only difference is that I've rotated my perspective here a little bit. So it's totally up to you. Active might have other thoughts on that. Active might say, do a chair flip, and you have to actually flip the chair from this to this. That's their software. It is the same molecule, just moving around it for a different perspective in 3D. It's good stuff, huh? This is truly the 3D conceptual side of this class. So I want to give you guys a quick second to get up and move around. And while I do that, I'm going to kind of pass this around. So if you want to try and feel out these chair conformations, here's my advice. Grab 2 carbons that are 1,3 to each other and flip them. And then grab the next 2 carbons that are 1,3 and flip them. You should be flipping them opposite from what your first flip was. And now you've gone into a different chair. Quite honestly, you're not going to get the hang of it in 5 minutes in class. You're going to have to build one of these and flip it for 10 minutes on your own before you start to kind of feel how that molecule is transitioning between its chairs and what that looks like. So if you're interested, pass it around, play with it a little bit. Let's meet back up here in no more than 4 minutes to keep going on. Hayden? I'll be back there in a second.
Can you double check this? I think I have it flipped from what you have. Because my H is on the down, you have your H on the down.
So here,
And it's going, they're the opposite.
this molecule is actually this. You are right. This chair conformation on your left is my chair conformation on my right.
So it's right, so this is still the right lower energy.
That's right. Yep.
But then here,
Now, your tert-butyl is on the right-hand side of your structure. My tert-butyl is on the left. That's a difference of just spinning this around.
even though the tert-butyl is on an up equatorial.
No, my.
here it's on a,
This is
oh,
my
that's
tert-butyl.
the tert-butyl. That's
Yeah.
okay, that's where I was getting.
I wanted to get like I already have to, you know, size them and
Yeah, so it makes sense. Yeah, to do both.
I know it is.
That's fine. I did it because I mapped it here. Here's carbon 1, here's carbon 4. Fine. Just because I wanted to.
So if you numbered number 1, number 4, then it'd have to.
But again,
I guess
I could have placed the numbers anywhere. The numbers are just a map to help you keep track of the position.
like intuitively I would
Yeah.
assume the turbulence. Because if that is this, and this or this, and I figured this would be at the end of there.
That's fine. You can take this
kind of the
molecule
opposite,
and you can rotate it around.
going from days to nights.
And now it
So,
would be
like,
positioned
my last little
opposite,
stretch of days and
where
nights.
this down equatorial CH3 is over here. This up equatorial tert-butyl is over here.
So then,
This is just one 3D perspective.
if we did it that way, then now it would be that way.
Well, that would give us kind of this structure, but
If I just
rotate it.
flipped
But if you wanted to show this conformation, where the two groups are equatorial, and you wanted to spin it around, it would still be an up carbon.
Yeah, what I drew is this exact thing, but just flipped over. Would that be wrong?
Well, let's see. Do your groups transition to it? You've got axial terbutyl, and then you've got equatorial terbutyl. Axial methyl, equatorial methyl. These are the two terbutyls. That's right. Absolutely.
That's the exact same as that, just looking at it differently?
It is.
I have no idea how that even works.
Then you got to convince yourself of it, and the best way to do that is build the structure.
Is that fine if I just
Absolutely.
choose-
Do you know what? If anything, that's the hardest part of being the grader. Is that I could give I could say draw the chair conformation for this, and there are 8 correct answers, maybe more, that you could draw, and I have
This
to.
is fine. It's fine that I don't understand that.
If anything, I would say build the molecule, get a modeling kit, and build it. Prove that you can look at it from that perspective, and that you can look at it from that perspective without flipping the chair at all, just by spinning it.
That one on the left would be mine on the right, right?
Yeah.
Would appear differently?
Yes, absolutely. Just rotate it around.
So this is 1, 2. That's also 1, 2. But you're saying they are different.
Yeah. And we'll talk about that next. Aiden, you had a question?
Yeah, I'm just suffering. Like I understand 1 through 4 exist, so they have to face the same way. However,
Well, you've got 1, 1, 4, 4 tetramethyl.
So if they take a question, yes.
it's 1 dimethyl.
And I was actually shocked, like,
And then the cis, we're going to talk about this in a second.
Yeah.
It says they're both wedged or they're both dashed.
Oh, so it's not symmetric.
Yeah, which is kind of orientation. They're both up.
Right. So I would say
Doesn't matter.
Oh,
Both are correct.
oh, thanks.
All right, you guys ready? Now that we have looked at the chair conformations for this compound, I want to talk about how we would tell apart these two compounds. I think you guys will agree with me that by taking this down methyl and having the structure oriented with an up methyl is going to change the chair conformations. Here's a down methyl, but if that's up, now I've got 1 equatorial, 1 axial. Here's a down methyl, but if that's up, I've got 1 axial, 1 equatorial. Those are different molecules, those two are. Just by changing the fact that the methyl group is dashed and the methyl group is wedged. So how do we name it to distinguish those two things? And how do we describe their relationship? Well, we're going to refer to this only with di-substituted rings. And this does go for all rings, not just cyclohexane, so we'll expand this in a little bit. We'll use cis to say that the two groups are both wedged or both dashed. Doesn't matter which one, they can't be distinguished. And we'll say trans to say one group is wedged, one group is dashed. I cannot use this naming convention on rings that have more than 2 groups. I can't even use it on linear chains. I might have a linear chain that has wedged groups or one wedged, one dashed. Linear chains do not get this terminology in the nomenclature. Just rings, just dye substituted. So this first compound, we would call it cis 1-tert-butyl 4-methyl. Boy, I'm sorry, my name is kind of like breaking out of the text box. Cis 1-tert-butyl 4-methyl cyclohexane. Correct? Thank you. What mistake did I make here? Those groups are one wedged, one dashed. They're not cis to each other. They're trans to each other. One is up, one is down.
And you don't include like the tert in your alphabetical name, right?
That's correct. Which is why butyl came before methyl, rather than tert-butyl coming before methyl. So I alphabetized by M and B. I think you guys would agree that it could have been 4-tert-butyl 1-methyl, but that's a tied locant set. Tie goes to the first alphabetically.
Why does the trans go before the one?
That's a good question. Where would you put it?
I thought it would go after the one.
Like 1 trans-tert-butyl, 4 trans-methyl?
1 trans tert-butyl 4 methyl cyclohexane.
I think trans clarifies both substituents, so it makes sense for it to go in front. 1 only clarifies tert-butyl, 4 only clarifies methyl.
Okay, so trans to them both.
Yeah, that's a good question. And here I'd have cis 1-tert-butyl 4-methyl cyclohexane. I told you guys that those prefixes were a pain. They take up most of that molecule's name. And now we can say, we can draw those 2 molecules differently. And we know that they have different physical properties. They have different chair conformations, different energies, a different preferred chair conformation. And we can take this down as small as we would like to. Can you name this compound? Give it a shot.
Trans 1,2-dibromo-butane cyclobutane.
Good. Trans 1,2-dibromo cyclobutane. The 2 groups have different orientations, 1 wedged, 1 dashed. The bromines are on positions 1 and 2. Could have given it 1 and 4, but that would have been the highest locant set. Cyclobutane. That's pretty clear, right? I mean, compared to conformations and Newman projections, that nomenclature is not too challenging. Now, these types of structures, like cis and trans, 1-tert-butyl 4-methyl cyclohexane, they're related as isomers. And I think you guys probably already have an idea of what isomers are. It comes from 2 words, actually, isomer, meaning identical units. You guys have heard of polymers. Polymers are multiple units. Isoelectronic species have the same number of electrons, identical. But there are a lot of different types of isomers. There are structural isomers. Although I want you to be familiar with their legal name too, which is constitutional isomers. Constitution meaning the buildup of the structure. Structural being a little bit more direct there. Structural isomers have the same chemical formula, different connectivity. Let's look at C6H14. There are many structural isomers here. One of them is N-hexane. One of them is 2-methylpentane. Same chemical formula, very different connectivity. Is this compound a structural isomer of these two? Why not?
Not enough room for hydrogens.
Not enough hydrogens. This has chemical formula C6H12. Different chemical formula. In fact, a lot of textbooks like to say that linear alkanes have this generic equation, CnH2n plus 2, and cycloalkanes have this general equation, CnH2n. Cycloalkanes and linear alkanes will never be structural isomers of each other. They have different chemical formulas. Good. Structural isomers also play into functional groups. For instance, one, two, three, four. 1, 2, 3, 4. On the left, I have a ketone. On the right, I have an alkene and an ether. Same chemical formula. Exactly the same. And I know that because they have the same number of sigma bonds, same number of carbons, same number of pi bonds. But they are connected incredibly differently. Sometimes those are referred to as functional class isomers or functional group isomers. But they are really just a type of constitutional isomer, a type of structural isomer. A bigger category here are stereo isomers. These not only have the same connectivity, they not only have the same chemical formula, but they share all of their structural connectivity. The first broadest class of this are cis-trans isomers. We already looked at the 1-tert-butyl 4-methyl cis-trans isomer pair. Here would be the cis isomer pair to our trans 1,2-dibromocyclobutane. You guys agree that they are connected in all of the same ways. Each carbon atom is bonded to all of the same things. But the arrangement in space, their spatial chemistry, is distinct.
If you just put one double bond on the linear chain, wouldn't it be a stereo isomer, a structural isomer?
Yes. Yeah, if I took out 2 hydrogens, and by removing 2 hydrogens, replaced it with a pi bond, then these would all be structural isomers. Which is kind of like this. I could give you another structural isomer for this compound. That looks pretty different, right? No pi bond to be seen. Same number of, same chemical formula. Exactly the same chemical formula. 4 carbons, 1 oxygen. We're going to talk at the start of our next unit about how that implies degrees of unsaturation. There could be more atoms bonded in that molecule, but there aren't. And we'll use that in our structural analysis. Okay, now let me ask you about this cyclobutane structure. Is this a stereoisomer to the other two? Why not? Different connectivity. The relationship on the right is actually a structural isomer to the two compounds on the left. And does this compound have a cis-trans isomer of its own? It is a di-substituted ring, but it's the same groups on the same carbons, so if you flip them, it'd be the same molecule. It doesn't have a stereoisomer. Now, these stereoisomers, these are what I call relationships. Oh shoot, the door got locked. Thank you, Hallie. We're describing relationships between molecules. The next type of relationship that we're going to see is called enantiomers. I'll be honest, I'm not sure what enanti means, but you hear the unit in there again, mer. Maybe somebody can look into what the first part of that name is meant to imply. The definition here is that these are non-superimposable mirror images. Did you know that everything has a mirror image? Everything has a mirror image, without fail. Some things are superimposable on their mirror image. Some things are not. Actually, many things that we deal with are non-superimposable. Writing makes mirror images non-superimposable because the mirror image is going to be written backwards or upside down. Your anatomical structure is non-superimposable with its mirror image because your aortic arch goes the other way in the mirror image. You can't take those two things out and superimpose them. One of the best, closest examples of enantiomers are your hands. These are mirror images of each other, but they cannot be superimposed. If I keep the palms pointed in the same direction, my thumbs don't overlap. And if I get my thumbs to overlap, my palms are not facing the same direction. I cannot get my hands to superimpose, though they are mirror images. So here's a challenging example. I'm going to keep this 1,2-dibromocyclohexane, and I'm going to draw its mirror image. It doesn't maybe look like its mirror image, but that's because the mirror plane that I'm drawing is actually going behind this first molecule and in front of that second one. I like to call this a back and forth mirror plane. This is dibromocyclobutane looking in the mirror and seeing its mirror image. This bromine on top is coming towards you. So in its mirror image, the bromine is going away from you. This bromine is going away from you, so in the mirror image, it's coming towards you. And now if you take these two molecules and you try to superimpose them, a bromine wedged doesn't superimpose with a bromine dashed, vice versa. And if I take this structure on the left and I try to flip it like a pancake, well, we talked about what happens with wedges and dashes when you do flipping. This bromine that's going away is going to get flipped so that it's coming at you. It's actually going to look exactly like this. It still cannot superimpose. Let me show you another way that we can show its mirror image. I can draw the mirror plane side by side. And now this mirror plane a little bit more clearly demonstrates. Oops, I forgot my bromine here. Their mirror image relationship. and they're still not superimposable. Obviously, if I take them over, my bromines are on the wrong side of the molecule. And if I take this molecule and I flip it like a pancake, this wedged group is going to be flipped so that it's dashed. It won't superimpose. I'm not saying that this is an easy job, taking two structures and seeing whether they superimpose or not. I'm saying you should go practice it when you go home today, because it takes a lot of practice to get used to that. But when we come back in tomorrow, we're actually going to look for tips, trends that we can identify that make it easier for us to predict. Are they enantiomers, or do they have some other relationship? All right? So that's where we'll pick up tomorrow, looking at more relationships between molecules. Have a good day, guys.